Welcome back to a new series from Learn Structural Engineering. In this presentation, I would like to cover an introduction to design of footings to cater for the effects of trees. Now look, this topic can be very complex and it may require hours of discussions. However, we hope to cover as much as possible throughout the coming videos. I had several engineers asking me to clarify and break down the tree design example that is presented in the Australian Standards AS 2870 on page 163, I think. So I had some feedback mentioning that there had been some confusion with the example. However, we will go through it step by step and see how the code has arrived at these results. The code gave some guidelines and procedures on how to cater for the effect of trees when designing footings. There are two main design methods that the code mentioned. The first one is called, we call it the code method, which is discussed in Appendix H under Guide to Design of Footings for Trees. Part H4 explains the procedures involved in the design. As you can see here, that there are several steps to take, such as A, B, C, D, and E, which is outlined in this design methodology. The worked out example shown in the code follows that same method. The code method primarily focuses on design of footings using a larger value of differential mound movement due to the effect of the tree or group of trees. So for a newly planted tree, we need to consider the differential mound movement for center heave, which is ym is equal to 0.7 ys plus yt, where ys is the normal profile soil characteristic surface movement without the effect of the trees, and then we add yt, which is the design tree movement value. To work out yt, we need to first determine the maximum potential tree movement from the tree induced suction profile, that dashed area here, which is basically yt max. So yt max can be calculated the traditional way, so by integration over the suction change profile previously, obviously taken into account the variation of the soil reactivity, which is the shrink swell index throughout the profile, as well as the alpha factor, which is the lateral restraining factor. And the alpha factor in this is generally taken as 1 due to the presence of the tree or trees, depicting the the soil profile to be fully cracked. With this method, we are focused on designing the footings to cater for an increase in strength and serviceability to withstand the soil interaction on a larger mound height. For example, say we have a normal H2 site with a YS value of 70 millimeters, then we would need to design a footing to cater for that center heave mound height of 0.7 times 70, which is 49 millimeters, whether we are using Welch or Mitchell's method. But if we have the effect of existing tree or group of trees, then we need to add this effect, which is yt, to 49 millimeters. For newly planted trees, we generally do not need to consider yt in the edge heave mound height. For edge heave design, the mound height ym would either be 0.5 ys if we are using Walsh's method, or 0.7 ys if we are using Mitchell's method. Now, if we are removing trees or allowing for the death of an existing tree or trees, then we would need to add YT to the edge heave differential mount height. Bear in mind though that the depth of design suction change, HS, is generally taken below finished surface level, below the cut and fill level, whereas the maximum design drying depth, HT, due to the tree, is taken below the natural ground level at the location of the tree. If we are using this code method, we must consider double-sided mount in our design, despite the location and the number of trees. For example, in this diagram here, we have a single tree at a distance dt from the slab, and dt is the minimum distance from the slab to the tree trunk. While one may argue that this is not really the practical case, especially when we have a single, a single tree on one side of the house, soil drying is just going to be under one side of the house. So realistically speaking, only a portion of the slab will undergo settlement due to the effect of the tree. And of course, it all sort of depends on the height of the tree and the distance away from the slab. I mean, we could have a very high tree, which the influence distance could affect the whole slab. So as it goes higher, the more it will affect radially around the slab. Now, drying of the soil by trees will affect the mound shape. It's important to understand that. Extra edge drying, therefore, edge distance will be significant only to one side of the building where the tree is located. Now, if we use this extra edge distance method, then we're basically converging or utilizing the South Australia group method, the Adelaide method. Then it would probably be reasonable to design for an unsymmetrical mound shape, which then becomes pretty complicated. However, if edge distances are not taken or not increased, then adopting the simplified assumption of the symmetrical tree affected mound may be conservative approach to compensate, if you like, for the change in the edge drying condition. When we work out the design mound height in center heave and edge heave, then we can then adopt a beam on mound model like the one we have here in this diagram, and then which we can assess the soil slab interaction. Nowadays, we can use some softwares such as Slug or Chord to model this, or we can even use a finite element software. If we have a slab, we can utilize a 3D plate or shell element analysis. Using Welch or Mitchell's method, we can then calculate the lift-off points, slab required stiffness to maintain the allowable design differential deflection, and also the applied resultant moment and shear distribution due to the superimposed loads counteracted with the soil stiffness as well. Once we consider all the applied loads, including the point loads at the edges and the point load in the center, then we can work out the resultant moment throughout the slab. Once we get all these results, we can then work out the slab section capacity and reinforcements to conform with the ductility and strength requirements of the code. The second alternative method is the Foundation and Footing Society of Victoria method. It is mentioned in the commentary section of the code. I believe it's in section CH5, page 166. Look, while it's arguable that the commentary section is just an informative section, as mentioned in the preface of the standard on page 2, I think, and does not form part of the mandatory body of the standard. At least this commentary section provides some information and advice. So it is extremely important to be careful when using the commentary sections to provide justifications for your designs. As you can see here, I highlighted it in red. The commentary to this standard has been included at the back of the document. The commentary is for information and advice only and does not form part of the mandatory body of the standard. And if you go a little bit lower, it kind of clearly says that the commentary is for information and advice only. In short, this Victorian method gives guidance on the tree affected distance and allows the footings to be suspended on piers or piles within area 2, as you can see here. And there is a pier depth for P1 and a pier depth for P2. Then the slab that is not suspended on piers, which is area 3, would have to be designed to cater for an additional movement from the effect of the trees. Okay, now this additional movement is almost linear. It looks a bit parabolic, but it's almost linear, more cubic, but it's almost linear here, distribution of 1.5 YT to YT. Or alternatively, the code suggests that we can continue the piers P2 with the same depth of P2 right through the area of P3. Now, how many of us design the rest of area 3 to cater for an additional movement of the trees? Look, I don't know. I know most of the designs appear only the affected area. However, if you really want to use the Victorian method, you need to use this methodology here. Now, we'll talk a bit about this Victorian method and do a step-by-step example in future videos in this series here. So please bear with us. So yeah, and then the third method, of course, we won't discuss this here, but it's the edge distance method, which is really called the South Australian or group method. And because the code hasn't really covered it thoroughly, it is covered in HB 26, the Residential Footing Design Handbook, if you want to go back and review it there. It is equally important to recognize that the current code method is essentially derived from the South Australia Adelaide method. The current code method recognizes different climate zones with respect to the depth of tree drying effects, as well as the corresponding suction change, or the suction change at the base of the profile, which obviously is caused from the effect of the trees. And this suction change, as well as the depth of drying effect, can vary from one climate zone to another. And like mentioned previously, the current code provided a simplified approach of a double-sided mound to compensate for that extra edge distance drying due to the effect of trees. Okay, wow, I think this introduction took a bit longer than what I expected. In the next video, we will get straight into that work example, which is at the back of AS 2870. And yeah, we hope you've enjoyed this video. Please subscribe and share and like so others may also learn. Until next time, we hope you have a great afternoon.